Okay, Mike, we have your permission to record and then broadcast your talk.
Yes.
As it is, with your permission, right?
Okay, yeah, sure.
Okay. So, okay, so we have 2 more minutes to go. Okay, I see that Raydon logged in.
Hello.
Hi, Raydon.
I may mute myself now.
Okay, no, I will make a very short statement and then get going. Because we said 9 o'clock, and then some people are probably trying to log in.
And it's past my bedtime.
Okay, sorry, Mike.
That's all right.
Oh, Chashu showed up. Hi, Chashu.
Hello.
Okay, we have almost 9 o'clock. Okay, we can get started. Hello, everyone. I'm Sean Lin from Brown University. This is the second of 3 lecture series by Professor John Michael Kosterlitz. Professor Kosterlitz is the 2016 Nobel laureate in physics, and today he's going to discuss vortices in 2D superfluid film, especially about the green function technique. Mike, you are on.
Okay, thank you, Sean. All right, so this is, as Sean said, this is the second lecture, and in this lecture, I will be a little bit mathematical, because what I want to do is derive a rather important thing, which is the so-called renormalization group equations for relevant to helium, superfluid helium films. Now, the reason for deriving this rather obscure thing called the renormalization group is because this is how one can actually get some exact results, measurable exact results for superfluid helium films. And so it's really worthwhile going through some of the details of the derivation. So for the first slide here, the thing about, remember, superfluid helium has got, is flowing, and its velocity, the velocity of the superfluid relative to the substrate is this V sub s. And because the superfluid velocity can be written as the gradient of the phase of the field describing the condensate. What this means is that the curl of the superfluid velocity can be written as exactly 2 pi h bar, where h bar is Planck's constant, divided by m, the mass of the helium atom, helium molecule, I beg your pardon, times an integer, and this z hat is just the vector pointing in the z direction, perpendicular to the film. So what really this says is that if I take a contour C encircling a vortex core, any contour encircling the vortex core, and I integrate the phase round this closed contour, it doesn't have to be a circle, it can be any shape, then this, the integral around the closed contour of d theta is 2 pi times an integer. With this integer n is, well, if there's no vortex present, n is 0, otherwise n is an integer, plus or minus 1, plus or minus 2, etc., etc. Now, of course, the superfluid velocity can also have a term describing smooth irrotational flow, which I write as just the gradient of a scalar, and they call the scalar phi of r. You know, r is just the position. Of course, because the curl of grad phi is, of course, 0, always 0. And so, and the result is we could write down a formula for the superfluid velocity, which is this equation here. It says h cross over m times the gradient of the phase, or the smooth part of the phase. That is just the smooth variations in the superfluid velocity, and there's plus the second term, which is the bit due to the vortices. So we've got an array of vortices at positions r prime with vorticity, this integer value field n of r prime, times this Green's function, g of r and r prime. Now, this g of r and r prime obeys the equation, basically Poisson's equation, del squared g, it's a second derivative with respect to, let's say, r, is just a delta function. And this implies, and I'll do the derivation actually in the next slide, because this derivation is quite important, but the result is that the Green's function is essentially just 1 over 2 pi times the logarithm of the magnitude of r minus r prime divided by a microscopic length a plus some constant of order 1. Now, of course, that expression is only true if I have, and there's actually bits, rather important bits of this Green's function which I haven't shown, but I will on the next slide. Now, the detailed derivation of the differential equation del squared g is equal to the delta function. I'm simply writing r minus r prime as r. Okay, so for this r, you can read r minus r prime. Now, if we take the Fourier transform of this g of r, which is just g of q, we can write the this Green's function, or solutions of a differential equation, as d2q over 2 pi squared times e to the I q dot r times g of q, and this g of q is just minus 1 over q squared. You see, because del squared, when I take the Fourier transform, del squared just becomes q minus q squared, and so I get the equation becomes a algebraic equation, minus q squared times g of q is equal to 1, because the Fourier transform of the delta function is just unity. And so we can write the Green's function as a function, and the Green's function actually depends only on the magnitude of its argument. It doesn't depend on the vector character. And this G of R can be written as -1/2π times the integral over the system. Now the system is of size L. L is the size of the system, and A is the size of the core of the vortex. And the core of the vortex, remember, is normal. So I'm only considering the what's going on in the superfluid. So what I get is Q dq over Q squared times this J naught of QR, where J naught of QR is just the 0th order Bessel function. And the important point is that this Bessel function, J naught of X, I just call the argument of the Bessel function X, I can approximate this by 1 if the argument is less than 1, and 0 if the argument X is greater than 1. So then I can write the Green's function as a function of R as just 1/2π times the logarithm of R over L, R over the system size. And then I can rewrite this as just 1/2π log R over A plus logarithm of A over L, which is a convenient way of rewriting this log R over L. Because eventually we're going to take L going to infinity. Sorry, keep on losing my cursor. Here we go. Okay, so then given that, I can write the Hamiltonian. Remember, the Hamiltonian of the system is just the energy of the system. It's the kinetic energy. So it's actually just 1/, its integral, it's a half K naught, for this K sub 0 is a constant which is proportional to 1 over the temperature, times the integral of the gradient of the smooth part of the phase all squared, this integral of grad phi squared, plus this other term, which is what have happened here? Sorry, I'm being dumb here. Right, plus this other term, which contains a triple integral. So is an integral over the vortex positions n of R1 times n of R2. So the gradient of the Green's function with argument R and R1 dotted into the gradient of the Green's function of R and R2. Now, doing this integral over these product of Green's functions, actually, part of it's very simple, because if I do the integral over this argument R, I can do an integration by parts, and what I get, this gradient term, gradient squared term becomes just the Green's function of R minus R1 times the Laplacian acting on the Green's function of R minus R2, R and R2, but that Laplacian acting on that Green's function is the delta function of R minus R2. So all this, so all you end up with is you basically end up with minus pi k naught times the integral of R and R prime over with R mod R minus R prime greater than the vortex core size times this logarithmic, or this Coulomb logarithmic interaction, and of course plus 1 or 2 extra terms. And these 2 extra terms are quite important. We have another term which is the energy due to the short distance behavior, which is just some constant, which I can call a core energy, E sub c times divided by kT times the total d2r of n squared of r. Now this core energy, E sub c, is, we don't bother calculating it because all we know about it is that it's some positive quantity and it's large. In general, it's much larger. We're assuming that we're at temperatures T such that EC divided by KT is much larger than 1. And then we've got this other term, which is pi K naught times the total vorticity, the integral d2r of n of r, integration of the vorticity field over the whole system, all squared, times the logarithm of L system size divided by A. Now, of course, when you have a large system, you're imagining L over A to be a very large number. So the log L over A is we take as basically infinitely large. So in other words, this last term is pi K naught times the total vorticity of the whole system, all squared, times the log times a very large number. But according to statistical mechanics, the energy or the probability of such a configuration of vortices is proportional to e to the minus the energy divided by kT. And so the last term, when L over A goes to infinity, gives us e to the pi K naught times the square of the total vorticity times something infinite. So in other words, the only configuration that will contribute will be when this total vorticity is 0. In other words, where this term inside the bracket is 0. So that means the total vorticity must be 0. In other words, the integral d2r n of r must be 0. So now if we were to restrict, as we will, the vorticity, this n's are 0, plus or minus 1, plus or minus 2, and so on. And so the argument now is, suppose that we're assuming that the core energy, E sub c over kT, is very large. And so this, when we put this thing into with a minus sign into the exponent to give us a probability, this would be e to the minus core energy over kT times the integral of n squared of r. Now, n squared of r takes on a set of values, 0, 1, 4, and so on, and 9, etc., etc., etc. And so if this EC over KT is a large number, then the only n's which will be have any non-zero probability will basically be n equals 0 or plus or minus 1. We can ignore n equals plus or minus 2, plus or minus 3, and so on. And so if we assume that we're only going to consider the lowest vortices, so the allowed values of n are 0 or plus or minus 1, then what we're saying is we're considering a system of a set of charges, say, because this is the nn log r minus r prime over a is a Coulomb interaction, it's like electrostatic interaction. So really what we're looking at is the problem of a plasma, a neutral plasma in 2 dimensions of charges plus 1 or minus 1. So that is the mathematical problem at hand. You see, if we do the statistical mechanics, the first term in the Hamiltonian, that obviously does nothing. It doesn't give us any phase transition. But the rest of it, as I said, which corresponds to a neutral plasma of plus charges and minus charges, that system might have a phase transition. Something interesting might happen to it. Therefore, the next problem is to investigate the statistical mechanics of a uniform electrostatic plasma. Now, of course, when the first time I came across this problem, did this derivation, was way back in the early 1970s. And of course, when I was very pleased when I managed to reduce the problem of interacting vortices in this superfluid helium film to possibly a problem which is slightly more understandable, i.e. this Coulomb plasma, neutral Coulomb plasma. But of course, solving the mechanics of a Coulomb plasma in 2 dimensions is also a very non-trivial problem. Now, another way of looking at it is to say, look, the phase, we're interested in the fluctuations in the superfluid order parameter, this complex field psi. Now, the magnitude of this field, that it doesn't have any fluctuations in it. So one can take the magnitude of the complex field to be given by some sort of mean field theory. So that's, and just take it as a constant over the whole film. And the only part of the order parameters that's varying is the phase, this phase theta. And we can write the phase theta as a smooth part phi plus this capital theta, which is a bit due to the vortices. And so we can write this capital theta at the point R as the sum or the integral over all the phases due to a set of vortices at R prime. And so one can write the phase at the point R due to a vortex, a unit vortex at the point R prime, as just the inverse tangent of y prime minus y divided by x prime minus x, because this is the solution. This is the solves the Laplace's equation in 2 dimensions. And then we can write the total Hamiltonian as the smooth part or the spin wave part, which is just the grad phi squared part, plus the vortex part, which we've seen, plus some interaction part, which is the interaction between any possible interaction between the smooth part phi and the vortex part capital theta. And so, formally you can expand this thing out as grad phi squared plus grad theta squared plus twice grad phi to grad theta. So the interaction part of the Hamiltonian is just k naught integral grad phi dot grad theta. And I can integrate by parts, and this just is minus k naught. So the integral of phi times del squared the capital theta, but that's 0 because del squared capital theta is 0. So in other words, there's no interaction between to this order, to lowest order, between spin waves and vortices. Okay, so here's if you like, is a picture drawn by my colleague Sean Sean Ling. And so take the vortex center, this little circle in the middle with a plus sign in it. And then the flow is, let's say, going in a counterclockwise direction. And so what we have is that if we're looking at the phase due to this vortex at the origin, no, so the phase, I beg your pardon, the phase at the point XY, due to this vortex at the point capital X prime and Y prime, this is what the picture looks like. And the angle, the phase angle, capital theta due to the vortices is precisely this angle between the x-axis and the line joining the observation point R to the center of the vortex. Come on. Okay, now, because we still want to understand the quantity we want to calculate is the so-called superfluid density, which is a quantity with the dimensions of mass density or mass per unit area. That's why it's called superfluid density. But it is the superfluid density is actually a part of a correlation function. Because a superfluid is not something you can put a bucket into a superfluid and take some of the superfluid out and weigh it. Okay, it is more complicated than that. And one thing one can to discuss the exactly how the superfluid, how to discuss the superfluid density in detail, which unfortunately we have to do in order to understand how to compute it. Okay, we think of two experiments. The first, so we think of a setup where we've got walls. These thick lines here are walls restricting the fluid. So the fluid is between the walls, and it's actually periodic boundary condition. We identify this boundary and this boundary. So it's like considering, if you like, the fluid on a tube. Okay. And then what we do is we move the wall or the substrate in the x direction at some fixed velocity u sub x. Okay, so one setup is where the walls are parallel to the velocity. The other setup is where the walls perpendicular, but we still move them in the x direction, which is in the horizontal direction at some velocity u sub x. Again, of course, periodic boundary conditions, we match this boundary with this boundary. Now, when we move these walls in the upper picture, when we move the walls to the right with a constant velocity, by definition of a superfluid, the superfluid is decoupled from the walls. So when the walls are moved, the superfluid does not move. And with the setup in the top figure. In the bottom figure, when we move the walls to the right, of course, the whole fluid is moving with the walls, because the wall is pushing the whole fluid along to the right. And so the whole, in the second situation, all the fluid is moving at velocity u sub x. Now, let's consider what's happening. We can always do a Galilean transformation and go into the frame at rest relative to the walls. And then, of course, in the upper figure, what's happening is the superfluid is then moving to the left. And in the lower figure, the superfluid is stationary because it's stationary relative to these walls. And so the free energy of the system, okay, in the laboratory frame, we call the free energy of the system F, and in the rest frame of the walls, we call the free energy F prime. And the relationship F and F prime is F minus u dot P, where P is the total velocity of the total momentum of the fluid, with just the integral over the system of the momentum density G of R. And of course, it's plus the P squared over 2m. Okay, so this is the free energy in one frame, and this is the free energy in the other frame. And of course, the superfluid momentum density, this GS of R, is just the integral of the energy, or the free energy, with respect to the superfluid velocity. And of course, this is just the parameter rho naught, the bare superfluid density rho naught of S times the superfluid density Vs of R. And by definition, the superfluid momentum density correlation function, we write in the form sorry. Okay. C alpha beta of the momentum Q times the parameter K and the other parameter Y. Y is the fugacity. And this is equal to, okay, to be absolutely, it's this constant h bar of mkt all squared times the correlation function, momentum density correlation function. And remember, of course, the momentum density is got two components. And so we consider just GS alpha, GS beta. And we can write this, decompose this correlation function into two parts. A part, a longitudinal part, and a part which is transverse to the velocity u. So we get A of Q times Q alpha Q beta of Q squared plus B, which is a function only of the magnitude of Q, times the transverse projection operator, which is delta alpha beta minus Q alpha Q beta over Q squared. And Now, one of the important quantities is this so-called stiffness constant, this which I call K sub R of T. And this quantity is in principle is measurable. And it is defined to be h bar squared times the measured superfluid density, which I call rho s of R, as a function of temperature, right? Well, R just means renormalized or measured, divided by m squared kt, and this is equal to the limit as q goes to 0 of the coefficient A of q minus B of q, where A of q and B of q are defined from the correlation function. And of course, this is not hard to see that this A of q is just k, which is just the parameter in the Hamiltonian, and the B of q is 4 pi squared k squared times the limit as q goes to 0 of the correlation function, the vorticity correlation function divided by q squared. And it's also a fairly simple exercise to show that I can write this thing in real space as k, which is, remember, is basically interaction constant, plus pi squared k squared times the integral of d2r over the whole system of just the magnitude of r squared times the correlation function n of r, n of 0. The vorticity, the correlation function of the vorticity at r times the vorticity at 0. Now, it's a little bit surprising that it's convenient to rewrite everything in terms of the correlation function in real space, but that turns out to be the best thing to do. Why is that? It is because one can calculate the vortex correlation function, n of r, n of 0, to order y squared. It's very trivial. Why is that? It's because, remember, that this correlation function is calculated as just the average of n of r, n of 0, n of r times e to the minus the energy of the two vortices, the energy of the interaction energy of these two vortices. And this is just, now, the minus sign, now, okay. There are two terms here in this to order, lowest order in the fugacity. We want two vortices. The first vortex, one vortex must be +1, and the other vortex must be -1, because the total vorticity has got to be 0. And the two terms, because if I choose one +1 and one -1, then I have another term where I just exchange the plus and minus charges. That gives me but one n is 1 and the other one is -1, so that gives me a minus sign. And then the two possibilities, that gives me 2. Then there's a fugacity squared, because that's the lowest order contribution, and the e to the minus energy of this vortex, the vortex interaction separated by r, is just r to the minus 2 pi k, plus terms of order y to the 4th, which we don't attempt to calculate, because we assume that the fugacity is very small, because the core energy we're assuming is very large. And so let us just make the assumption that we can stop the perturbation expansion of this correlation function to lowest order in the fugacity, which is just the first term here, minus 2y squared r to the minus 2 pi k. And because other contribution of order y to the 4th. then we can write a perturbation expansion for this normalized stiffness constant. And it's more convenient to write the perturbation expansion for the inverse function 1 over k of r. And this is equal to, we're doing a perturbation expansion, remember, in the fugacity, assuming that the fugacity is very small, which is correct self-consistently, as we'll see. And this is just plus 4 pi cubed y squared times this integral. Okay. Integral from a to infinity r over a to the 3 minus 2 pi k. The 3 comes from r squared, the 2, and there's an r dr here, so that gives a r to the 3rd power. And this correlation function is r to the minus 2 pi k. And of course, we've got terms of order y to the 4th. Oh, sorry, this is just definition, I should have been written down earlier, of the momentum density, the relation between the momentum density in real space and the momentum density in Fourier space. So this is just the relation between them. Now, remember we have this expression for the renormalized stiffness, or one of the renormalized stiffness, as a perturbation expansion up to order y squared, fugacity squared. And the complicated term was the integral from the smallest value of the separation, which was a, up to infinity. But suppose we just do a simple rescaling of the cutoff a, and we rescale the cutoff to become a e to delta L. And so delta L is very small, so I can write e to the delta L as 1 plus delta L. And so our perturbation expansion becomes k to the minus 1, which doesn't change, plus 4 pi y cubed, and the integral now runs from a e to delta L, the new cutoff, to infinity. Dr r to 3 minus 2 pi k, divided by remember, it started life as the old cutoff, right? But since the lower limit of integration is now the new cutoff, I have to replace the old cutoff by the new one. So just the denominator becomes a e to delta L to the power of 4 minus 2 pi k. And of course, I want to cancel out this the extra part e to delta L times 4 minus 2 pi k. So I just put the term in the numerator, and the bit of the integral from a to e to delta L, which is missing here, I just calculate and add it on. And that's very true, very simple, just 4 pi cubed y squared times delta L. Remember, we're only working to order delta L. And so we rewrite this as, so we take the first term, k to the minus 1, plus the second, this last term, 4 pi cubed y squared delta L, and we write k to the minus 1 plus 4 pi cubed y squared times delta L plus 4 pi cubed y squared times 1 plus, we expand e to the 4 minus 2 pi k delta L as 1 plus 4 minus 2 pi k times delta L times the integral. Okay, then we can say that this expression is actually exactly the same as the original expression, except that k to the minus 1 has become k to the minus 1 plus delta k to the minus 1, and y squared has become y squared plus delta y squared, where the change in k to the minus 1 is just 4 pi cubed y squared times delta L, and the change in y squared is just 4 minus 2 pi k times y squared delta L. Now, so I haven't actually done anything. Now you take a deep breath and swallow hard, and you make the following argument. We regard the coupling constants, k and y, as scale-dependent coupling constants. In other words, we regard them as depending on the scale factor L. And so under the small change, L goes to L plus delta L, we can say that we can rewrite this change in inverse K as a differential equation. Dk to the minus 1 by dl is equal to 4 pi cubed y squared plus order y to the 4th, and dy by dl is just 2 minus pi k times y squared plus order y cubed. Now, you can say to yourself, all right, these equations are okay as long as this fugacity y is very small, because the correction terms are if the y is very small, the correction terms which we haven't calculated are presumably even smaller. So let's solve these differential equations, which is not difficult, and ask the question, does this fugacity y remain small for all values of L or not, or does it not remain small? And the solution to the renormalization of equations is best shown graphically. So if I plot the fugacity y of L on the vertical axis and the parameter k of L, and remember k is proportional to 1 over the temperature, then what happens is, suppose we start the system off with a Hamiltonian given by with parameters some k naught y naught, in which are correspond to being in the somewhere in the right-hand corner, right-hand side of the diagram. Now, we notice that if pi k is precisely 2 for all values of the scale parameter L, then dy by dl is 0, because the coefficient of y on the right-hand side is 2 minus pi k. And so if pi k is greater than 2, then we Y and K are related by one of these lines, which flow to this axis, which corresponds to Y equals 0. There is one straight line solution to this equation, or the two straight line solutions, and one of them is just pi k equals basically is just a straight line which hits the y equals 0 axis at some special value of k. In fact, it happens to be 2 over pi. If k is slightly smaller than this critical value, the flows basically look the same to start with. The flows go parallel to this straight line, but then the y does not, the fugacity y does not go to 0, but it turns around and starts increasing. And so basically we have a set of flows in this ky plane, which look like the picture here. And the physical interpretation of these flows is quite simple. It means that all the systems with parameters lying in this bottom right-hand corner flow to y equals 0, which corresponds to, and y equals 0 means that this is a superfluid system, because y equals 0 means there are no vortices, therefore it's superfluid. Okay, and so this straight line must correspond to being at the critical temperature. In other words, Tc is a function of y naught. You see, what we've really done is we parameterize the system as a collection of vortices with fugacity y. And it's slightly, if you're slightly above the critical temperature, you corresponds to one of these flows which go parallel to the critical line and then bends around and shoots off to large values. And of course, all the flows starting with parameters, below this, above the straight line going to 0 corresponds to being t above is some value, parameter values above Tc. And so we can interpret every point above the straight line in the bottom right-hand corner as being a system above the critical temperature. In other words, normal fluid, because all the systems correspond eventually to large values of the fugacity, which correspond to, probability of having free vortices of being of order 1. So in other words, free vortices being present, which corresponds to a normal fluid. Systems in the bottom right-hand corner of this diagram correspond eventually to y equals 0. In other words, no vortices, therefore this is interpreted as being a superfluid or being below critical temperature. Now, I didn't, just a minute, see if that's, I think that's the last slide. Yeah, I want to talk a little bit more about this. Of course, when we integrate these differential equations, there's an integration constant which I call C, and this C is can take on various values. It can be positive, negative, or 0. And the flows which correspond to these lines which go to y equals 0 corresponds to a value of this integration constant, which is positive, and it also corresponds to little t, which I call t minus tc over tc, just a fractional deviation from the critical temperature, also corresponds to t negative, and those below tc. And these region 2, which is above these straight lines, correspond to this integration constant being negative, and this t minus tc being positive, but less than this value 8 pi y naught. And this right-hand segment of the diagram corresponds to c positive, the integration constant being positive, but the t minus tc is larger than some constant, which happens to be 8 pi y naught. Okay, and so now the point is that what really these renormalization group flows show you is that this system does have a phase transition. And the system is parameterized by this integration constant c, which can be expressed in terms of t minus tc and the physical fugacity. For some reason, I forgot to write down the expression. I'll write that down for the last lecture. And as I said, the interpretation of these flows as L increases is that what it does is, as L increases, you end up with a new system. It's equivalent to the starting system in a sense, but it is a system described by a different set of parameters. It's exactly the same Hamiltonian, but with different parameters. Different interaction parameters k and different fugacities y. And then it's a matter of interpreting what these flows or these mathematics actually means physically. And the natural interpretation is that Hamiltonians, which have parameter values k naught, y naught, which correspond to being below this straight line here, flow to some constant value of k, but y equals 0. And y equals 0 means in the renormalized system there are no vortices present, because the fugacity of these vortices is 0, and therefore we interpret it as a superfluid system, but is below Tc. A Hamiltonian corresponding to a k naught and y naught, corresponding to just above the straight line. These Hamiltonians, under this rescaling procedure, flow, the fugacity comes down just like below Tc, but then turns around and climbs to large values. And large values of the fugacity means that vortices are there, are there. They've got a high probability of order. They're present in the system with probability of order 1. And if you've got vortices present with a probability of order 1, that means that the system is not superfluid, because there are free vortices around which would dissipate any flow, and therefore it has to be interpreted as a normal fluid. So therefore, all the systems which flow to large values of the fugacity up here correspond to a system, a normal fluid, or if you like, the fluid is above the critical temperature. The only line we still have to interpret is this straight line that flows to a point y equals 0 and some special value of k, which is actually pi over 2. And this line, straight line here on the right, we have to interpret as being exact at t equals tc. So any Hamiltonian lying initially on the line flows to the special value of k and y equals 0. And so therefore any point on that straight line corresponds to a system at the critical temperature, and is Tc, which is a function of the initial fugacity y0. Okay, now really that, and of course all other systems, yeah, I say all systems to the right, to the left of this line flowing to this critical line corresponds to being in the high temperature disordered phase. And now, of course, we still have to do some real non-imitation calculations, because actually all a normalization group calculation actually does, it says that a system, a physical system with a given set of parameters, k0 and y0, is equivalent to this renormalized system with the new parameters k of L and y of L. That's all it says. And the interpretation depends on the rest of it, whether it's a high temperature phase or a low temperature phase, depends on your physical interpretation. I've given you a bit of a physical interpretation, but in the last lecture, we'll discuss in more detail how we can actually do real calculations of various physical quantities, physical correlation functions. And in particular, what I want to show is that the superfluid density or superfluid mass per unit area, it actually at Tc, in other words, corresponding to the straight line here, actually what happens is that the superfluid density, the measured superfluid density at a temperature just below Tc divided by Tc is equal to some universal calculable constant. It's expressible in terms of parameters like the Planck's constant, the mass of the helium molecule, Boltzmann's constant, and so on and so forth. In other words, it is a quantity that's known exactly, and therefore, since the superfluid density, mass per unit area, and the critical temperature are in principle measurable, this enables a confrontation of theory with experiment. And the prediction of the ratio of the superfluid density just below Tc to Tc is a calculable constant which you cannot, within this theory, you cannot change. No matter how you play around with the Hamiltonian, you cannot change that quantity. And so that prediction is if you like, a smoking gun prediction on which the theory on which the measurement of which the theory stands or falls. Okay, now that's not finished my lecture. And so on Friday, I beg your pardon. For you guys it'll be Saturday morning, but for me it'll be Friday night. I will talk about some of the predictions, the measurable physical predictions of the theory. And okay, so thank you for your attention, and I hope you learned something.
Okay, so thank you, Mike. The lecture is very clear. Thank you. Martin, can you pick questions?
I'm logged in there and waiting, but it's still not finished yet. Yeah, okay, it's finished. So maybe we can wait a little bit about questions.
Okay.
No, sorry, if there are any questions, I'm happy to try and answer them.
Yes. So because Mike, I cannot see the Chinese platform. I cannot open. So Martin can. So he will pick any questions from the audience. Okay. And but there's a 1 minute 60 seconds delay on the China side. So.
So that's the advantage of giving a very clear lecture. There aren't many questions. It means the lecture is either incomprehensible or very clear.
Yeah, well, it's very clear this time. Yeah, filling in all the details, it really makes a difference.
So Redo, I suppose that they should type in, and I'm going to see something.
Okay.
Redo?
Okay, so how about this, Martin? This is late, so why don't we let the student also post questions to you, ask the student a question to you, and then they can you can share the questions with Professor Kosterlitz, and Mike will answer it in the third lecture. How's that?
Yeah, it's pretty fair. I'm typing in. I'm see there are any questions.
Because this time delay, it does create a bit of a
yeah, I totally understand.
Yeah, confusion here.
I have seen a lot of familiar names. The person attended this this talk so far will be 3,111.
Wow, 3,111. Wow. Okay, can you send me a picture of that? I would like to see that. That's a record. Mike, I think Mike must be thrilled. Okay, so why don't we do this? It's very late and Mike is tired, and so why don't we end today's lecture here? So I'm gonna pause, I'm gonna stop the recording, and then Martin, why don't you share with Mike the questions you get from the students and then the audience or the professors in China, and then Mike will answer them in the next lecture on the July 16th, this Friday here in America, but in China will be July 17th, 9 a.m.
Saturday morning, right?
Yeah, Saturday morning, okay? All right,
Yeah.
okay, so let's thank Professor Kosterlitz one more time, and then I'm gonna end the talk right here, okay? Okay, thank you. Thank you, everyone.
Thank you, Mike. Thank you, Mike.
Welcome.
Yeah, thank you for the 3,111 people for logging in, okay?
Okay.